So, I decided to do my project on an issue that I find to be increasingly important in today's society. I decided to research a comparison of the performances of petroleum-based plastics with their bioplastic counterparts. So, before I get into that, let me start with some background information. Plastics are made up of chain-like molecular structures known as polymers, which are made up of even smaller repeating units known as monomers. Polymers can be artificially created and very easily manipulated, which makes them the perfect building blocks for plastics. Plastics are, as I'm sure you know, increasingly important staples of modern society. They are convenient to manufacture, they're extremely affordable, and they're also extremely versatile. However, all of this does not come without a price because plastics do not degrade over time like natural resources do. This is where bioplastics come into play. Bioplastics are plastics made up of naturally occurring polymers. Polymers can be found in nature in things like cornstarch, molasses, vegetable oils. So bioplastics are plastics made up of those. And a lot of people consider bioplastics to be healthier for the environment. So why aren't they more heavily employed? It's simply because they're a younger technology, they're far less advanced, they're more expensive to manufacture, they're less convenient to manufacture. But one question I have is how does their performance compare? Which brings me to the purpose of this presentation, which is to compare the effectiveness of plastics and their respective bioplastic counterparts. So, in order to do this, I divided the project into 4 separate experiments, each looking at a different plastic and a different task. So the plastics I tested were low-density polyethylene, polyethylene terephthalate, and polypropylene. And the bioplastics I looked at were polylactic acid, a sort of plant-based polyethylene terephthalate, as well as a material made of synthesized wheat fibers. So low-density polyethylene is a very flexible and elastic material, so it's commonly used in things like plastic bags, or in this case, sandwich bags. So what I looked at were Ziploc sandwich bags and PLA wrap box sandwich bags, and I was testing the air sealing capabilities of these plastic bags. I did this by cutting up apple slices and putting 4 slices into each bag. As you can see, I have 4 bags of each material, as well as a 9th group of exposed apple slices, which was meant to sort of act as a controlled variable. The status of these apple slices was monitored daily for a week. A short log was taken detailing their status every day, as well as a photo was taken, and they were checked for any discoloration as well as any mold colonies. And those last 2 bullet points were what was used to quantify the data. Experiment B also looked at low-density polyethylene, only this time I was looking at the tensile strength of them because they are also frequently used in garbage bags. So again, being compared to PLA, I hung the bags from a hook, as you can see in the image there, and then I added weights to the interior of the bag in order to test the tensile strength. And these weights, each added weight became progressively lighter than its preceding weight in order to increase the precision of the experiment, and the weight that the bag held before it was ripped is what was used to quantify the data. Experiment C looked at polyethylene terephthalate, which is commonly used in things like plastic water bottles, which is what I'm testing here. And the bioplastic counterpart is this thing called a plant bottle that Coca-Cola, Dasani's parent company, released. It's essentially, chemically, it is still PET, but it's made up of naturally occurring materials. So it's chemically still PET, but it's more organic plastics. So that's what I'll be using for the bioplastic counterpart here. And I'll be testing the water vapor barrier capabilities, and I'll be doing this through what's called an evaporation test. So what I did was I weighed each of the bottles before anything. I took their initial weights and then I put them on that cookie sheet, as you can see in the image here. And then I put them in the oven for an hour at 170 degrees Fahrenheit, which is the lowest my oven can go. And then I took them out, weighed them again, let them cool for an hour, weighed them again, and then I just repeated that process until I started to see some significant weight loss from either bottle. And then the total weight change is what was used to quantify the data from this experiment. Experiment D was looking at polypropylene. Polypropylene is frequently used in reusable plastic containers like Rubbermaid or Tupperware containers. So as such, since it's meant to be used over and over again and put in the dishwasher over and over again, I figured it would be appropriate to test its durability against corrosive cleaning products. So what I did was I submerged the two containers into a bleach solution, which was 2 gallons of Clorox bleach and 4 gallons of distilled water. I put it in there for a week. And much like the apples in Experiment A, I monitored their status daily. I took a short log of them every day, and I also thoroughly dried them and weighed them every day. And their total weight change is what was used to quantify the results. So, the results from these experiments. Experiment A, the logs detailed that by day 2, beads of moisture had begun to collect on the interior of the bags. By day 3, the apple slices had begun to curl up around the edges and deform. And by day 6, the first mold colonies were discovered. So as you can see in the chart here I have in the top right, the discoloration on that custom-made scale, it was about the same for the first 3 days within the two groups. And then by around day 4, PLA started to discolor a little more rapidly, and it sort of branched away from the traditional plastic bags. And by the end, on average, PLA had rated about 1.75 points higher on that discoloration scale. And I did a t-test to make sure that these were statistically significant figures, and the p-value was below the alpha level of 0.05, so they are statistically significant. Experiment B actually got some surprising results from this. The PLA bags, on average, held about 2 kilograms more than the LDPE bags did. And I recorded that while I was adding weight, the PLA bags seemed to stretch a lot further. They were much more elastic than the plastic bags were, which I believe to be the reasoning for why they ended up holding more in the end. Again, I ran another t-test on this, and again, the p-value was below the alpha level of 0.05. Experiment C was also pretty interesting because in the first few cycles, the bottles all actually gained weight, which is what inspired the idea of having multiple cycles anyways. So as you can see, all the bottles maintained pretty steady weight for the first 4 cycles, and around cycle 5, that's when I started to see some significant weight loss from the plant bottles, and then that weight loss became more exponential throughout the next few cycles, whereas the PET bottles maintained a steady weight throughout all 7 cycles. So on average, the plant bottles ended up losing about 7.15 grams more than the PET bottles. And also, all the bottles underwent some physical changes. They all sort of got punched out at the base, as you can see in this image here. And I ran another t-test on this, and again, they are statistically significant figures. Experiment D ended up being inconclusive. There were no quantitative results collected, meaning that there was no weight change in either container over the week. However, there was some strange physical reactions. Around day 2, the bleach solution, as you can see in the image on the left here, became very cloudy, and it maintained that for the rest of the experiment. And as you can see in the right here, the walls of the polypropylene container became a little discolored and began to develop some ridges around the edge. So despite those two things, there was no weight change in either container. So conclusion to be drawn from this. Experiment A, the LDPE bags had more effective air sealing capabilities than the PLA bags. Experiment B, the PLA bags were able to hold more weight without breaking. Experiment C, the traditional PET bottles were able to contain more water and maintain a steadier weight than the plant bottles. And experiment D was inconclusive. So before I draw my final conclusion, I would like to first acknowledge that there was definitely a margin of error in these experiments, because firstly, it's important to acknowledge that some of the results could have been due to the engineering flaws in the designs of these products rather than from the materials themselves, and also just due to lack of equipment and funding, and due to the fact that I'm only a high school student. It was a pretty primitive experimental environment, and though I did my best to minimize error, there's still going to be an understandable level of it. So the final conclusion is, while bioplastics are useful in certain circumstances, the technology is simply not as developed, nor as versatile as petroleum plastics, and they are therefore not yet a suitable substitute for widespread consumption. So some potential improvements that could be made on these experiments, maybe a vacuum sealer for experiment A in order to minimize any air that might have been trapped in the bag. For experiment B, maybe a mechanism that could cause some sort of constantly increasing tension on the bags rather than these lump sum weights. For experiment C, just all around less variables, a more similar bottle design, more similar bottle size. Maybe the minerals in the water that these companies add for taste could have had an effect on the results. And for experiment D, maybe more concentrated bleach in a more controlled environment, because I had to leave that container of bleach outside just because it's not safe to keep that kind of thing inside. So the cold temperatures may have had an effect on the results. So I would like to acknowledge Mrs. Baker and Mrs. Morrison for providing the guidelines for this experiment. I would like to thank my dad, who lent his material science expertise to me when I was coming up with and executing these experiments. And I would also like to thank my friend Riley Slisher for proofreading a lot of the literature that I wrote for this experiment. Here are my references. I'm just going to assume you have some questions. So one question that people frequently ask is, how are plastics modified? Well, things called additives are implemented into the polymers in order to change up how the plastics act. So there are 4 common types of additives. Plasticizers are meant to modify the glass transition temperature of plastics. Colorants are pretty self-explanatory. They're made to change the color of the plastics. Reinforcers are made to make the plastics stronger. And stabilizers are what are responsible for making plastics so permanent. They are what keep plastics from aging and deteriorating over time. There's a lot of confusion about is bioplastic biodegradable? The answer to that is not always. There's a lot of nuance around the term biodegradable, and some people could say, yeah, it is biodegradable in very specific conditions, like specific temperatures and humidity levels. One solution to biodegradation was that was developed a while ago is a thing called oxo-biodegradable, which it's actually terrible for the environment because it doesn't break down the material fully. It just breaks it down into little nanoparticles, which you get that in the compost, and then it gets into the food systems and the water systems, and it's just all around worse for the environment. So a more important question is it recyclable? PLA, which is one of the earliest forms of bioplastics, is not very effectively recyclable. It messes up the system. But this plant bottle that Coca-Cola has released it's highly recyclable. It's in the recycling system, pretty indistinguishable from traditional PET. So that's where a lot of people are looking for future sources of innovation. One thing that has a lot of questions is, how can one get plastics from plants? Well, it's actually a pretty similar process to getting traditional plastics. It's building the monomers and then polymerizing them, turning them into polymers, and then building plastics out of those polymers. The only difference is that these monomers that are being built out of organic materials rather than petroleum-based materials like in traditional plastics. And finally, is there hope to improve on bioplastics, seeing as they're pretty primitive right now? The answer to that is simply yes, absolutely there is. Plenty of countries are investing lots and lots of resources into the innovation of bioplastics. And it's a constant source of innovation. It's constantly growing. And though it started small, as the concern for the environment with traditional plastics and their impact on it grows, so too does the innovation around bioplastics. So yes, there's lots and lots of hope to improve them.